The topic for Lesson 1-2 is properties of real numbers. You'll learn how to classify real numbers and use the properties of real numbers to evaluate expressions. How is the distributive property useful in calculating store savings? Manufacturers often offer coupons to get customers to try their products. Some grocery stores try to attract customers by doubling the value of the manufacturer's coupons. You can use the distributive property to calculate these savings. As it looks on the receipt, we've got 2 discounts for 30 cents, 2 for 50, 2 for 25, 2 for 40, and 2 for 15 cents. It would be simpler just to go 2 times the sum, which if we add those up, I get $1.60. And 2 times $1.60 is $3.20. Less ink used this way. All of the numbers that you can use in everyday life are real numbers. Each real number corresponds to exactly 1 point on the number line, and every point on the number line represents exactly 1 real number. Real numbers can be classified as either rational or irrational. The word of rational is ratio. A ratio is the comparison of 2 numbers by division. A rational number can be expressed as a ratio, m over n, where m and n are integers, and n is not 0. The decimal form of a rational number is either a terminating or repeating decimal. So 1/6 is a ratio of 1 to 6. 1.9 could be written as 19 over 10, so it's a ratio. 2.57 looks like repeating, is a ratio. -3, square root of 4, which happens to be 2, and 0. A real number that is not rational is irrational. Prefix ir means not. The decimal form of an irrational number neither terminates nor repeats. So square roots that don't come out even, such as the square root of 5. Pi is a famous irrational number that repeats forever. And then they have a decimal repeating in a pattern. They're just adding another 0 between the digits, but it is a non-repeating, like 0.0101, that would be repeating. Or terminating is going to go on forever. So those would be 3 examples of irrational numbers. The sets of natural numbers start with 1, 1, 2, 3, 4, 5, and keep going forever. This little ellipsis means it's going on and on and on, the dot, dot, dot. Whole numbers adds 1 number, which has a hole in the middle, so it adds 0 to our natural numbers. Integers are whole numbers and their opposites, so it goes forever in both directions. Are all subsets of rational numbers. Whole numbers are a subset of rational numbers because every whole number n is equal to n over 1. The Venn diagram shows the relationships among these sets of numbers. So all natural numbers are whole numbers. All whole numbers, which include naturals, are integers. All integers are rational numbers, and those are all subsets of real numbers. The opposite of rational is irrational, and they are also subsets of real numbers, but those 2 groups are mutually exclusive. You can't be both rational and irrational at the same time. So examples of irrational numbers, we said square roots that don't come out even, so square root of 3 or pi. Rational numbers could be lots of things. Let's go, an exotic one would be -5/3. It's a fraction and it's negative. Integers can be positive or negative, so it could be 3 or it could be -3. Whole numbers, we have those listed out, so it's 0 through all the counting numbers. And then natural numbers were also called counting numbers, so I can't quite fit them in there, but 1, 2, 3, and so on. The square root of any whole number is either a whole number or it is irrational. For example, the square root of 36, well, we know what that is. It's 6, so 6 is a whole number. But the square root of 35 is somewhere between 5 and 6, so it is irrational. Name the sets of numbers to which -2/3 belongs. Well, -2/3 is a ratio, so it's a rational number, and all rational numbers are real. Integers can't have fractions or decimals, so if it can't be an integer, it can't be anything else further in the Venn diagram either. Again, 9.9 repeating, it could be written as a ratio, so it's going to be rational and real. There is something that is not a real number. It's called an imaginary number that we'll get to later. The square root of 6 does not come out even, so that one's going to be irrational. And once again, these are all subsets of real numbers. You could graph it on a number line. The square root of 100, we could simplify to 10, so that's going to go clear in the center of our bullseye. It is a natural number. That's a number we could count things with. So all natural numbers are also whole numbers. All whole numbers are also integers. And all integer numbers are also rational numbers. And all rational numbers are all real. So if we get a nice easy number like that, we get a long list of categories it falls into. Negative 23.3 is a decimal, so it's going to go out to the edge of the bullseye where it's just rational. And all rational numbers are real. They can be graphed on the number line. In Algebra 1, we spent a lot of time building up all of these real number properties, and even before Algebra 1, I think. The commutative property says it doesn't matter the order that I add or multiply in, I get the same answer either way. The associative property says if I leave things in the same order, I can move where my parentheses are in either adding or multiplying. The identity property says who you are doesn't change if you add 0 or if you multiply by 1. The additive inverse, if you add opposites, you get 0. And the multiplicative inverse, if you multiply a number of times its reciprocal, you get 1. Distributive property, Santa distributes gifts to all the good children at Christmas. So, and it doesn't matter if the A is first or if it's at the end. We're still multiplying each thing inside the parentheses times what's outside of it. Name the property. They added negative 8 plus 8 and got 0, so that's the additive inverse. This time they took 5 times 8 and 5 times 6. That looks like distributive property. The additive inverse for negative 7 is positive 7. And the multiplicative inverse of negative 7 would be negative 1/7. Okay, before we do the additive and multiplicative inverse for square root of 1/9, the square root of 1 over the square root of 9 would simplify to the square root of 1 is 1, the square root of 9 is 3. So the additive inverse or opposite of 1/3 would be negative 1/3, and the multiplicative inverse or reciprocal of 1/3 would be 3 over 1, which is the same as 3. Next, we need to look at ways to apply the distributive property. Audrey went to a post office and bought 8 34-cent stamps and 8 21-cent postcard stamps. How much did Audrey spend altogether on the stamps? Okay, so we could just simplify it as it's written. Using a calculator, 8 times 34 cents is $2.72. 8 times 21 cents is $1.68. And when we add, we get $4.40. We could have also done the same problem using the distributive property. And so we could have rewritten that as 8 times 0.3434 cents plus 21 cents, which would be 8 times 55 cents, which, wouldn't you know, is $4.40. Same answer, two different methods. I'm going to simplify using the distributive property. We're going to take 4 times both terms inside those parentheses, and then 2 times both terms inside of the second parentheses. So we have 4 times 3a minus 4 times b plus 2 times b plus 2 times 3a. 4 times 3a is 12a minus 4b plus 2b plus 2 times 3a is 6a. Combining our like terms, 12a plus 16a is 18a. Negative 4 plus 2b, negative 2b. The a's and b's are not like terms, so we are done. In summary, real numbers can be classified as rational or irrational. Those nice rational numbers can be classified as natural, whole, and or integers. And we looked at how to use the properties of real numbers to simplify algebraic expressions.